Hello and welcome everyone to our tutorial on Immersive Imaging Technologies, where we will cover the whole imaging pipeline from capture to display. Okay, let's start by introducing ourselves. My name is Emin Zerman, and I'm a postdoctoral research fellow at Trinity College Dublin. Currently, I'm working on visual perception and quality estimation of various immersive imaging technologies within the vSense research group led by Professor Alyosha Smolich. I did my PhD in signal and images at Telecom Polytech in France. My research interests are human visual perception, image processing, and image and video quality assessment. Now, my colleagues Mata and Chare will also introduce themselves.
Hello everyone, my name is Alain, and I'm a postdoctoral researcher in the vSense project in Trinity College Dublin, where I'm currently working on live field imaging. Before that, during my PhD, I worked on image and video compression using image restoration techniques, and I'm more generally interested in image and signal processing, computer vision, and computer graphics.
Hello everybody, I'm Çağrı. I'm a senior research engineer at Samsung Research UK. Previously, I was working at Trinity College Dublin. I did my PhD in multimedia signal processing and communication, and my research interest is machine learning, computer vision, and immersive multimedia technologies.
The idea for this tutorial came up while three of us were working together in the vSense research project. Therefore, I'd like to introduce vSense project team. vSense project team consists of more than 20 researchers, and we are working towards extending visual sensation through image-based visual computing. In addition to the topics of this tutorial, the project team also works on visual effects and animation, as well as deep learning for visual computing. Here is the outline. The tutorial will start with an introduction to immersive imaging technologies, which is this part. Then we will continue with different stages of the imaging pipeline, such as acquisition, content delivery, display, and perception. Let's start with part 1, immersive imaging technologies. In this part, we will try to give answers to these three questions. What is immersion? What are immersive imaging technologies? And what are the applications? Therefore, this part is divided into three main points: the definition of immersion, different imaging modalities such as light fields, omnidirectional imaging, and the applications for these technologies. Okay, so let's start with human experience. We experience the world in two different ways, real or virtual. The real experience is directly related to our sensory experiences, and it is our daily lives. On the other hand, virtual experiences can be either sensory or non-sensory. Non-sensory experiences are dreams and daydreams, and sensory ones can be triggered by hearing a story, reading a book, or watching a movie. Imaging technologies are developed to store visual information on a permanent or semi-permanent medium. Pinhole camera is the most basic type of camera. Then came photography, and the photos are taken on photographic plates, analog film, and then most recently, images are stored digitally. This enabled the information transmission in great distances and enabled telepresence. The term telepresence was coined by Marvin Minsky in 1980 and refers to the phenomenon that a human operator develops a sense of being physically present at a remote location through interaction with the system's human interface. Then, presence is defined in a broader sense as being there in a mediated environment, including other virtual experiences. Lombard and Ditton include various factors which would affect presence. One of these parameters is immersion, which is defined as a concentration to the virtual environment instead of the real world and loss of time. And for completing this circle, we have also the tele-immersion, which is the interaction or presence of people from different places in virtually the same environment. Within the timeline of imaging, from Lumiere Brothers' Train, which was one of the first moving films which impressed a lot of people, to having audio in the films, to color films, and eventually high dynamic range imaging, every big step brought more viewer immersion. Current state-of-the-art immersive imaging technologies extend visual sensation, augment the viewer presence, and provide the viewer with a higher degree of freedom. Before we go any further, let us introduce the different degrees of freedom. Let's start with the two basic concepts, 3 degrees of freedom versus 6 degrees of freedom. Although 3DOF can also refer to the position of degrees of freedom, which is the moment in XYZ in space, in the context of immersive imaging, it means the enabled rotation over the 3-axis. This is yaw, roll, and pitch. While 6 degrees of freedom includes both position change and rotation change, where the spectator is allowed to move in the space wherever he or she likes. We also have two different terms which would sit in between these ends, which are 3 degree of freedom plus, which is 3DOF plus, and Windows 6 DOF. So 3D DOF plus is basically it enables a limited spatial movement for spectators within some boundaries, where Windows 6 degree of freedom is essentially the same thing with 6 DOF, except with a handheld, with the help of handheld display. Traditional imaging pipelines are designed to acquire and display visual media on planar surface. Instead, we have different imaging modalities now, which vastly change the viewscape. To answer our second question, what are immersive imaging technologies? Let's first consider the planoptic function. The 7-dimensional planoptic function measures the intensity of the light seen from any point of space in XYZ, any angular viewing direction, theta and phi, over time t, and for each wavelength lambda. The planoptic function remains a theoretical concept, which immersive imaging modalities aim to replicate or approximate based on some simplifications or assumptions. For example, the radiance of a light ray remains constant along its path through empty space. Usually, wavelengths are also sampled by RGB color rendering. Light field imaging aims to consider the light as a field, much similar to electromagnetic fields. However, for practical reasons, it is mostly simplified. The most commonly used simplification is the two parallel planes parametrization. In this context, the light rays are parameterized by their intersection with the two parallel planes. In turn, this helps acquiring the light field. The two parallel planes parametrization implies that one plane represents different camera position and the other plane represents image or sensor plane. The camera plane corresponds to different imaging angles and it captures parallax as shown on the left, but the viewing frustum is limited. Once captured, the original scene can be rendered for the user with realistic parallax, increasing the immersion, for example, by giving depth information to the viewer. Omnidirectional imaging systems instead capture different viewing angles over time. Typically, the 360-degree camera is fixed and it captures the world around the camera. Ideally, all the rays coming from different parts of the sphere are captured. Here you see a sample omnidirectional video. The captured omnidirectional image or video can be then visualized using different displays, such as a head-mounted display, or it can be 2D smartphone or tablet as well. Since the captured content is spherical, its use in various imaging stages is not really straightforward. We will discuss this in the next part. The volumetric video or free viewpoint video gives the user the full 6 degree of freedom, and it is the best approximation of the planoptic function, which can be seen from any position, from any angle, and over any time. So here you see a sample volumetric video, which is fixed on a location and the camera is rotating around them. And with this kind of freedom at hand, we can use these volumetric videos and free viewpoint videos in augmented reality and virtual reality applications. Volumetric videos are generally acquired in dedicated studios with multiple cameras looking inwards, like these ones. The generated volumetric videos can be used in either augmented reality or virtual reality applications. Here, two examples of these applications are shown. On the left, you see a simple augmented reality application which uses volumetric videos in Snapchat, which places them in the real world. And on the right, you see a very simple virtual reality environment which was visualized via an HTC Vive with a volumetric video placed within. The limitation of the volumetric video is, though, it generally looks inward and captures objects and people, but not the environment itself. Lately, the boundaries between different modalities are disappearing. The goal is to achieve full 6th degree of freedom. To achieve better approximations of the planoptic function, i.e. that is, being able to reproduce the light from scene faithfully, these different modalities tend to be merged together. This is an omnidirectional light field from Google's Welcome to Light Fields VR experiment, which is available on Steam. So as you can see at the beginning of the video, it starts with the light fields, but then you can still move your head within some limited boundaries and limited boundaries in space, and you can still have some kind of 3DOF plus experience. Let's try to answer the third question. What are the applications? The immersive imaging technologies can be used in many different applications such as entertainment, education, communication, and even novel storytelling applications. One of the first applications to come into mind is entertainment. It is also the one topic that creates a lot of attention for the end users. Many sports events are already captured using a large number of cameras from different angles. Using the immersive imaging technologies, these sports events can be converted into 3-viewpoint videos, which then can be used in augmented reality like shown in this video, or virtual reality applications. Another item for entertainment can be drama and theater. Similar to the transition from traditional theater to TV for drama, a new transition will begin to understand the mechanics of this new medium. Recently, Samuel Beckett's piece titled Play has been recaptured as volumetric videos and re-envisioned in both augmented reality and virtual reality. Here you see the video showing the steps for this creation. This play is very interactive in its original form, and as you can see from the figure above, there are 3 people who died and came to the purgatory, talking about their past lives. The spectator or viewer actually chooses the person which then starts talking by shining a light on them, and the user can change the light to a different person at any time. Therefore, it is a play which is easily adaptable for this new medium. Another example is a performance called Awake One, which is a piece this is also created in virtual reality environment, and it makes use of acquired imagery instead of computer generated images. The immersive imaging applications can also be used for post-processing. Here you see a post-production application which modifies the lighting of the scene. For this application, a point cloud is generated from 9 different light field cameras. The artist can then change various elements on the scene, such as lighting or other elements. Here you see an interactive relighting application in which the artists added a different light source to the scene which is already generated from different cameras. Also, other applications might include computer games and various other entertainment applications. The immersive imaging technologies can be used to augment education with realistic representations and/or simulations, which can be then used for employee or student trainings. These can range from medical education to mechanical parts assembly and even to drama education. Another educative application could be using immersive imaging in museums as museum guides. Here you see such an application. Above, the volumetric video generation process is depicted, while below, a user using the augmented reality application is shown. Now imagine that you can use an AR app with a life-size volumetric guide rather than just an audio guide. So these kinds of applications will help people have better museum experiences, and it could be really educative. Communication is another important and valuable venue for the immersive imaging applications. We need to communicate, and now more than ever, we are communicating mostly from our homes with the coronavirus situation all over the world. Here are 2 different examples. The first one is immersive communication with holoportation, which was developed by Microsoft. With this prototype technology, a 3D volumetric model of your body and that of your partner or family member are created, and these are displayed to the other side with the help of a HoloLens head-mounted display. A second example is remote collaboration, and during the announcement of HoloLens 2, spatial is also mentioned as the remote collaboration platform, which can be used in many different devices such as HoloLens, Magic Leap, even PCs and phones. With this, collaborators from different parts of the world can work as if they are sharing the same space. The immersive imaging technologies also allow us to come up with novel storytelling approaches. One example is Bridging the Blue. Bridging the Blue is an immersive creative experiment that explores virtual reality as the ultimate empathy machine, where users can explore an imaginary world and experience personal representations of clinical depression. It is essentially a meditated, perspective-taking experience of VR. To make my point clearer, I would like to show you a part of it.
I hadn't been depressed for over 7 years. This time it started with sudden demolition works. New owners of the downstairs maisonette had decided to refurbish before they moved in, without mentioning it to me. There was daily dust, noise, vibrations, and what I experienced as bullying.
As you see, this new storytelling approach merges together a volumetric video, a virtual reality environment, and originally composed music in order to convey a certain emotion. To summarize, in this part, we've discussed the key concepts about immersive imaging, such as the concept of immersion, the planoptic function, and the degrees of freedom definitions. We've also introduced different imaging modalities, such as light fields, omnidirectional imaging systems, and volumetric video systems. And we've mentioned the various applications for these technologies. Now that we've presented the theoretical concepts, we will see that in the next part, how to capture immersive images and video in practice. This concludes the first part of this tutorial. Now I give floor to my colleague Martin for part 2, and thank you for listening.
In this part, we're going to see how to actually capture visual data for immersive imaging in practice and the main associated data formats. So there is a wide range of systems and devices for capturing immersive imaging data, and we're going to focus on the imaging modalities introduced in part 1, that is light fields, omnidirectional imagings, and 3D models and volumetric videos. They all have in common that they aim at sampling or subsampling the planoptic function. And for the sake of this presentation, I'm going to divide the systems into two main categories. So first, we'll start with a system which is based on a single camera. This can be a traditional 2D camera or a more advanced design. And then we'll see systems which are based on multiple cameras. Note that the intention here is to provide an overview of the main existing systems, but not an exhaustive list. Here is a high-level list of the different systems based on a single camera for the different imaging modalities that we consider in this presentation. First, we'll see systems which are based on a traditional 2D camera, which obviously cannot capture immersive imaging in a single shot, but it is possible when moving them around. Then we'll see some more advanced designs for a single device which can capture light fields or omnidirectional videos in a single shot. First, let me introduce some basic concepts about 2D cameras. So one of the very first camera design to ever exist was the pinhole camera, which consists of a pinhole and an image sensor, typically a film. And light rays from the real world are projected on the image sensor through the pinhole. This kind of camera is easy to model with just a few parameters. We have the intrinsic parameters, which basically describe the relation between the camera center and the image sensor, and the extrinsic parameters, which describe the position and orientation of the camera. Altogether, the intrinsics and extrinsic parameters allow to connect points in the 3D world space to image pixels coordinate. And because this model is linear, it can be summarized in the matrix form. So here we see the intrinsic matrix K. The extrinsics are summarized in a rotation matrix R and a translation vector T. And when multiplied together, we obtain a single projection matrix P for the camera. which can be used to project a 3D point with coordinates x, y, z to a 2D pixel coordinates u, v. And this kind of model and the knowledge of its parameters is very important in any application for which we need to know where is the camera with regards to its environment. And for example, it's essential when doing 3D reconstruction from multiple views or depth space view synthesis. And it's certainly essential to know these parameters when dealing with most immersive imaging systems. In practice, this means that one of the first steps for any of these applications will be to run some kind of calibration to estimate these parameters. Obviously, we've stopped using actual pinhole cameras a long time ago and replaced the pinhole by a lens. And the lens will take light rays emitted from a point in space over different angular directions and reconverge them onto the sensor where they are integrated on a single pixel, as long as the point, the object point, is in the depth of field of the camera. So this is interesting because it's in general improving the signal to noise ratio. And for example, it allows to take pictures in low light conditions or with a faster shutter speed. And we can see that this is still equivalent to having a single light ray going through the lens center, which means that the pinhole camera model is still valid, although we might need to add some parameters to correct some of the lens distortions. The other interesting thing we can notice here is how we are losing the angular information of the different light rays with the 2D camera, as the light rays emitted from the different angles are all integrated on a single pixel. So obviously, a single shot from a 2D camera is not enough for immersive imaging capture. So when we use a 2D camera, we're going to have to move it around to capture light rays coming at different angles. And this idea has been used for light field capture since probably the beginning of research on light fields. And the position and orientation of the cameras has to be controlled very precisely, which usually involves a robotic system. So in this example and animation here, we showed an example for capturing light fields parameterized with two parallel planes, where each perspective view is captured one at a time. This way of capturing two parallel plane light fields is interesting because we can obtain really close viewpoints, so we have a very dense sampling of the angular dimension. But one of the drawbacks is that we cannot capture dynamic video content using this technique. So here are different examples of such systems. On the left, we have a robotic arm for spherical light field capture implemented at Stanford in the early 2000s. In the middle, we have a Lego gantry, also implemented at Stanford a few years later, for two parallel plane light field capture, where the camera can only move up and down and left and right. With this system, the light fields have a resolution of 17 by 17 views and around 1000 by 1000 pixels per view. Finally, on the right, we have a diagram of a system implemented in the Fraunhofer IIS lab more recently, where the light fields capture have a resolution of 101 by 21 views, and each view has a 4K resolution. So this illustrates well the dense sampling that can be achieved by such system. Despite the robotic systems, the orientation and position of the camera is never perfect, so it usually needs calibration and rectification. Once the two parallel plane representation is enforced, the good thing about this representation is that intrinsics and extrinsics parameters for each view can easily be derived from the light field parameters, which, for example, can be the baseline between the views and the distance between the two parallel planes. And this will also be true for camera arrays. So similarly, we can capture omnidirectional imaging data with a single camera by rotating the camera around, and this allows to make again strong assumption on the position and orientation of the camera. So each 2D view will capture a limited field of view of the full sphere with some overlap in between the views, so that they can then be stitched together into a single omnidirectional image. So in this example, we're showing what actually corresponds to a panoramic capture, but full spherical setups are also possible. It's fairly easy to implement nowadays, and there are readily available motorized platforms which can be controlled with a smartphone. For the stitching process itself, there are usually 3 main steps. So first, we have a registration step, for example, using feature matching between the images. Then a warping step where different images are aligned, and finally a blending step where different images are merged into a single image. And one important consequence of the stitching process is that we lose the parallax between the different images. So it really is like we have a flat image on a sphere and no sense of depth, which corresponds to the 3 degrees of freedom. Nowadays, most of us own a smartphone, so we essentially have a camera in our pocket. And there are more and more methods for immersive imaging capture based on smartphones. In general, there are no robotic control of the camera, but instead the camera is handheld. So there is no prior information on the orientation and position of the camera. This means that the systems usually rely on simultaneous localization and mapping techniques, also called SLAM, which allow to keep track of the position and orientation of the camera in the environment, while at the same time estimating the 3D geometry of this environment. So on the left here we have an example of light field capture, which is based on an application which helps guide the user toward the best sampling position. And on the right we have an example of real-time 3D mesh estimation from a company called Abound Labs. And the advantage of these systems is their ease of use, but again, they are limited to static scenes. So now that we've seen some examples of systems based on 2D cameras, we're going to see some more advanced designs which allow to capture the different immersive imaging modalities that we consider in this presentation in a single shot, and potentially allow video capture. So this first example is developed by a startup company named Cadence and is based on the paper cited at the bottom. And it consists in a novel lens design which can be mounted on any DSLR camera. And the core idea is that in this lens there is a so-called image multiplier, which is highlighted here in red. And this is a tube with a square cross section made of mirrors. And this so-called image multiplier allows to reflect the light rays arriving from different angles and capture them at different pixel positions on the sensor, unlike a traditional 2D lens. So here we show an example of a raw image as it appears on the sensor, which looks a little bit like a kaleidoscope. But if we look closer, we can see that this raw image can actually be divided into a 3x3 sub-images, which corresponds to different viewpoints, with some of the images flipped along the horizontal and/or vertical direction. So this lens, when mounted on a DSLR, allows to capture 2 parallel plane light fields in one shot, and can also theoretically capture videos. And one of the limitations of this device is the limited angular resolution, and also the fact that the spatial angular information has to be multiplexed on a single sensor, which limits the resolution of the individual views. And so examples of these individual views are shown here on the right and reflect the different viewpoints of the scene. Another well-known design for capturing light fields is the plane-optic camera, also sometimes called lensless camera. There are 2 main brands of such cameras, and the first is the LightRAW, although this brand does not exist anymore and the production has been discontinued. And there are also ray trace cameras. So if we look back at regular 2D cameras, I mentioned earlier that the angular information is lost as it is integrated on a single sensor pixel. So the main idea behind the plane optic camera is to introduce an array of microlenses in between the main lens and the image sensor. And we can see that by doing this, the light rays coming from different angular directions are redistributed onto different pixels on the sensor. So a plane optic camera captures a two parallel planes light field, and the number of microlenses correspond to the resolution of a single viewpoint image, while the number of pixels under a microlens corresponds to the number of viewpoints. So like for the Galens design, there is a trade-off between spatial and angular resolution, since the whole spatial angular information is multiplexed on a single sensor. Similarly to traditional 2D cameras, we can define a so-called plane-optic intrinsic matrix H. But contrary to the intrinsic matrix of 2D cameras, which establish a correspondence between a point in 3D wall coordinates and a 2D pixel index, the plane-optic intrinsic matrix connects a 4D ray in wall space indexed by the light field two parallel planes indices, ST, U, and V, to a 4D pixel index A, J, K, L. And in this case, I and J are relative pixel indices under each microlens, indicated here on the right, and K and L are indexing the microlens directly. I'm not going to go into the details, but the matrix H itself is a 5x5 matrix, and its coefficients depends on the plane optic camera parameters. So the distance between the main lens and the microlens array, the distance between the microlens array and the sensor, the number of microlenses, the number of pixels on the sensors, the focal length of the main lens, etc. There are two main designs for plane optic cameras, and the first one is called plane optic 1.0. And it corresponds to the case where all the microlenses have the same focal length. And this is the kind of design which is used in light raw cameras, for example. With this design, it's fairly straightforward to rearrange the raw image on the sensor into a collection of 2D images corresponding to the different viewpoints. Here is an example of light field capture with a light raw camera. And on the left, we're showing a raw sensor image. And in the zoom-in part, you can see individual microlenses images. So as I just mentioned, this raw image can be rearranged into individual viewpoints, and this is shown on the right here. And we can see a typical artifact of light fields capture with a plane optic camera, which is that the images on the border are darker than in the center of the light field. And this is due to the lens vignetting effect, where less light is getting through the lens at its edges. Another limitation with the light raw camera is that it is not possible to capture videos. The second design of plane optic cameras is called plane optic 2.0, or sometimes focused plane optic cameras. And it corresponds to the case when individual microlenses can have different focal lengths. This is the design that's used in the ray trace cameras, and in the case of ray trace, there are three different values for the microlenses focal lengths. With this design, it is a bit more complicated to decode the raw image into 2D viewpoint images, as it requires depth information. So a depth map has to be estimated from the raw image directly, which can be a challenging task. However, it's been shown that this design can improve the depth of field of the camera as well as the effective resolution of the images captured. Here we show an example of plane optic 2.0 data captured with a ray trace camera, which is able to record videos. Again, on the left, we have the sensor video with zoom on individual microlenses images. And on the right, we have on the top 5x5 viewpoints extracted from the raw video. and on the bottom the video corresponding to the center view. Now that we have seen how light fields can be captured with a single device, let's see some specific cameras designed for omnidirectional images and videos capture. There are two main types of design, either based on a curved mirror or a fisheye lens. An example of design based on a curved mirror is shown in the middle, and here the shape of the mirror is an hyperbola, but other shapes exist, such as the parabola or an ellipse. And the idea is that light rays coming from all surrounding directions will be reprojected through the mirror onto the camera image sensor, as illustrated in this figure in the middle. So we cannot capture the whole sphere directly with such design, but it has a large field of view, usually superior to 180 degrees. The second design relies on a similarity, but is implemented with a fisheye lens, as shown here in the figure on the right, which again allows to redirect light rays coming from all surrounding directions onto the camera sensor. The field of view for a fisheye camera is usually around 180 degrees. So it is possible and quite common to capture the full sphere by combining two fisheye lenses. An example of such image capture with a Samsung Gear 360 camera is shown on the left. And you can see that the whole surrounding room has been captured on a single image. As for traditional 2D cameras, it's very useful to have a model which allows to connect 3D world space coordinates to the 2D pixel coordinates. So obviously for omnidirectional cameras we cannot directly use the pinhole camera model, but the unified spherical camera model is the one commonly used. And it's valid for both mirror-based or fisheye-based cameras. In this model, we have a first step where a point in 3D space with coordinates x, y, z is first projected onto the unit sphere centered at the camera position. And only then we can use a perspective projection to project that point onto the camera sensor. And this is computed with a matrix generally named K, similar to the intrinsic matrix in the pinhole camera model. But the center of projection is here shifted from the sphere center and the camera center as shown on the right. That shift parameter will depend on the mirror shape or the fisheye lens used. Now at this point in the presentation, we've seen several systems which can be used to capture immersive imaging data using a single camera. And these systems are in general fairly easy to implement and easier to use, but they suffer from limitations. For example, systems based on a single 2D camera cannot be used to capture videos. So here we are going to see more complex systems based on multiple cameras, synchronized cameras recording at once. All the different imaging modalities listed here can be captured using these systems: light fields, omnidirectional imaging, and volumetric videos. The first example, which is shown here, is a system designed to capture spherical light fields, where multiple GoPro cameras are mounted on an arc, and this arc is rotated around an axis. Similar to single camera system, it cannot be used to capture videos, but it can reduce the acquisition time compared to a single camera. And this is the system that was used to capture data for the Google VR experiment called Welcome to Light Fields, which was mentioned in part 1. This is a follow-up work from Google, which is still aiming at spherical light field capture for VR, but here they have settled for a different trade-off. So they are not capturing the full sphere, but instead they have cameras mounted on a portion of a sphere, which is physically translucent, so the camera can see through. And with such systems, they are able to capture videos. This idea of using a ring of camera to capture light fields is not new, and it's been used for years now to capture parallel plane light fields. For example, on the left, we have a 12 by 8 camera array from Stanford, designed in the early 2000s. In the middle and on the right, we have more recent examples with a 4 by 4 array from Technicolor and 8 by 8 array from Saarland University. So the results which we obtain is fairly similar to having a single camera on a gantry, but the main difference is that here, using synchronized cameras, we can actually capture videos. So this comes with some limitations. For example, the physical space occupied by the cameras usually means that we cannot capture very close viewpoints, and only a sparse sampling of the angular dimensions is possible. Also, these kind of systems can be very bulky compared to a single camera system. And in addition to the camera array itself, it usually needs to be operated by powerful computers and even servers to store the large amount of data that is generated in a short time. Multiple cameras can also be arranged in a circular or spherical setup in order to capture omnidirectional videos. And here we show two examples. On the left, a system designed by Google, and on the right, a system designed by Facebook. And they're both aiming VR application. So again, video capture is the main purposes of these systems. And they are designed to be more portable than the light field camera arrays that I just presented. In particular, if the images are stitched, then they require less data storage than individual views. Finally, contrary to omnidirectional systems which are looking outwards, we have multiple camera systems looking inwards, which can be used for 3D models and volumetric videos capture. They are usually implemented in a studio setup, which have recently become fairly popular for volumetric content creation. Every studio is different and uses a different configuration for the cameras and the background. But all these studios use RGB cameras, sometimes combined with infrared cameras or depth sensors. For illustration, we have here on the left a picture of Microsoft's Mixed Reality Capture Studio. On the top right, we show the Volucap studio based in Germany. And on the bottom right is the studio of Vologram, which is a spin-off company of the Vicens project, located here in Dublin. In addition to the studio setups, it is also possible to have more portable and lightweight solutions, for example using multiple smartphone video cameras, although the quality might not be as high as what can be achieved with the studio setup. So here we show another example from volumetric content from Vologram, where they use 6 smartphones video cameras to capture the subject. So I've just presented a wide range of techniques and systems to capture immersive imaging content. But note it is also possible to combine some of these systems together. For example, here we are showing that multiple planoptic cameras can be used together to create planoptic multiview or planoptic panorama contents. Another example of such a system is the FTV 360 project from INRIA, which is using a set of omnidirectional cameras spread inside a scene and captures synchronized videos. And this can then be used to render full 6 degrees of freedom content. So now that we have seen how to capture immersive imaging content, I'm going to introduce the main data formats and representation associated with the different imaging modalities. And they range from pure image-based representation for light fields to geometry-based for 3D models and volumetric videos. I want to make clear that I'm going to talk about data representation before any encoding or compression, as this will be discussed by my colleague Cagri in the next part. By definition, light fields are a collection of images, and the most common representation is to have an image corresponding to each viewpoint, as shown on the right. When captured with a plenoptic camera, it's also possible to use the raw sensor image, but this image can also be rearranged into the multiple viewpoints. So any existing image format can be used to store this data as long as it supports the bit depth of the content. For example, the bit depth of Lightrow is 10 bits, so typically 16 bits PNG format can be used. In addition, it's also possible to store metadata such as the intrinsics and extrinsic parameters for each viewpoint, or the light field parameters such as the distance between the two parallel planes. In the case of omnidirectional imaging, we still have a pure image-based representation, which again means that we can use any existing image format to store the data. However, since this image is supposed to be located on a sphere, we have to project it onto a planar image representation first. One of the most common ways is to use the equirectangular projection, shown here, or the cube map projection, but there are other projections available, such as the octahedron projection or the isocahedron projection, which we show here now. And obviously the resulting planar image is very different from one projection to the other, and that can have an impact on the following encoding performance. Finally, when using 3D models or volumetric videos, we need to introduce some geometry, and that can be represented using two different formats: textured polygonal meshes or colored point cloud. The geometry itself is computed from the input image, and how to perform the geometry estimation is a whole other topic that we won't have time to cover today. But this is where a good calibration and estimation of the camera model is very important. First, for the textured meshes, it consists in a surface with vertices and faces and an image texture or atlas, which is mapped onto the defined surface using what is called a UV map. So here we have an example of a mesh, and on the left image you can see vertices which are highlighted in black. A useful file format is the wavefront OBJ, which contains the vertices 3D coordinates x, y, and z, the UV coordinates on the texture atlas, and the face information with the associated vertex and texture coordinates. So here we have a sample OBJ file on the right, and it starts with the material file at the top. Continues with vertices, the vertices texture or the UV coordinates, and the face information. For the face information, we have n different vertices and texture coordinates, which are specified as shown here, which helps 3D model reconstruction. So this is a sample material file, which was specified at the top of the OBJ file. And it includes various lighting values, such as the ambient light, the diffuse light, specular light, transparency, etc. Finally, we have the image data, which contains the texture atlas, shown here on the right. And you can see that this atlas does not look at all like the original images, but it does contain every piece of image texture that is needed to be mapped on the mesh surface. The atlas is usually packed into a more compact representation, as shown here, and this image can then be stored using any existing image format. For colored point clouds, each point's 3D coordinates in space is stored, sometimes along with some attributes. Obviously, for a color point cloud, we need the color information, but it can also be the normal vector for each point, for example. In most cases, the Stanford PLY format is used to represent colored point clouds. And here we have an example. This header on the right indicates that this PLY file contains the X, Y, Z coordinates, the RGB color information, and the normal vector coordinates. Here we have the rest of the file, and the columns corresponds to the different parameters described in the header, and each row corresponds to a different point. Another format which we thought could be interesting to mention here is the Universal Scene Descriptor, USD in short, which is an open source format developed by Pixar. It can be seen as a container format used to describe a 3D scene in a hierarchical manner. And it's becoming quite popular in the content creation industry, such as the visual effects community, architecture, design, robotics, manufacturing, and others. One of the reasons for this success is that it's compatible with a range of tools and software already in use in the industry, and it allows people to work at the same time together on the scene without overwriting other people's edits. So to conclude this part, we have seen that there is a wide range of techniques and systems to capture immersive imaging data, either based on single 2D cameras, specific camera designs, or multiple cameras. And all these systems have in common that they are trying to sample the plenoptic function. In particular, they are trying to capture light rays coming from different angular directions. So all these systems capture a lot more than can be seen at once. And this has two main consequences. First, these systems generate a lot of data. And in the next part, my colleague Cagri is going to explain how to encode and transmit this data. And the second consequence is that we will need specific rendering algorithms and/or displays to visualize this data. And my colleague Emin and myself will talk about this in part 4.
In part 3, we will talk about the content delivery for immersive imaging technologies. In particular, we will see how to compress and stream immersive videos. I will start with a core idea of adaptive video streaming system. Adaptive streaming system is a technology that is designed to deliver a given capture video to the users in most cost-efficient way possible and in the highest quality. In adaptive video streaming system, we first encode a given capture video with multiple encoding target bit rates and resolutions. We then encapsulate the bit streams generated by the video encoder to a streamable format like MP4. This format can be played at the user device. Another important file is the manifest file that contains a set of rules like requesting low video quality or highly compressed video for low bandwidth range and requesting high video quality for high bit bandwidth range. Based on the manifest file, the user device can request an optimal video quality level from the server. Now let's focus on video coding, which is the core element in an adaptive streaming system. Without encoding, raw format of capture videos use lots of space. It is not a practical solution to store or transmit them with their original format. Therefore, we need a cost-efficient compression solution. This slide shows rate distortion curves of the main video coding standards developed over 20 years. Even though all of these standard codecs use same operation blocks, the coding efficiency is getting better and better in each time. For example, the latest video coding standard, High Efficient Video Coding, HEVC, provides 50% bitrate reduction compared to its previous standard, Advanced Video Coding, AVC, at the same quality level. This part of the tutorial has three main sections: light fields, 360-degree video, and volumetric video. In each session, we will discuss coding, and streaming solutions. Let's start with light fields. Light fields represent very large volumes of high-dimensional data, and there is a need for designing cost-efficient compression algorithms. Many solutions are already available, and most of them adopt standard image and video compression solutions to light field data. On this slide, you can see a delivery pipeline of light fields. The first block is the acquisition, where we capture light fields using number of cameras. The captured light fields is then rearranged at the representation block. Next, we encode light fields using video codec and store or transmit them to the client side. The client side, the device can decode, render, and display the transmitted bitstream. Now let's first talk about light field coding. There are a number of light field coding solutions. There are coding techniques based on sparse subset, based on standard video coding, based on multi-view video coding, and solutions in JPEG Plano standard. Let's focus on light field coding based on a sparse subset. In the idea of such coding, only a sparse subaperture images are encoded, like the corner ones, and missing ones are reconstructed at the decoder side. There are several examples in literature. One example is reconstruction using Fourier disparity layers, called FDL. The FDL model consists of a set of additive layers which can be simply shifted and summed to render a view of the light field at any angular coordinate. In the proposed compression scheme, a subset of light fields views is first encoded with traditional video compression solutions like HEVC. An encoded subset is used to construct a Fourier disparity layer model. And missing views can be reconstructed with this model at the decoder side. Another example is to use graph-based representation. Using graph-based representation, we can exploit correlation between subaperture images. In this work, a subset of light field called layer 1 on the slide is first extracted from 4D light field, and graph is estimated for the complete light field structure. A graph is a data structure characterized by a set of nodes or vertices. The key idea is to estimate how similar each subaperture image and represent that similarity as a connection weight between each subaperture image. At the decoder side, these weights can be used to interpolate the missing subaperture images. There are also coding techniques using standard video coding. Differently from the previous part, in this coding techniques, all subaperture images are stacked together as a video and can be used with standard video coding. Here, coding performance depends on the subaperture image order. As can be seen on this slide, the captured light fields are arranged as a temporal sequence of image follow a specific scanning order. Here the main aim is to exploit the temporal correlation with a regular video sequence. This structure is suitable to be coded with standard video coding solutions, HEVC. Therefore, both spatial correlation and the correlation between neighboring views or video frames can be exploited. The coding performance of such coding technique depends on the order. As you can see on the slide, there are many scanning orders available in literature. There are also light field coding techniques that use multi-view video coding standard, such as MV-HEVC or 3D-HEVC. In these techniques, 2D prediction structure is designed to better adapt to subaperture images. Therefore, both spatial correlation within an image and the correlation between subaperture images are exploited. There is one good example where the authors propose a new coding prediction scheme that uses a hierarchical organization of the input light field views that assign a specific level to each frame based on its location in the 2D grid. And the method can use MV-HEVC to achieve good performance. Coding standardization bodies are also active in this field, such as JPEG. JPEG developed a JPEG Plono reference software that contains two coding solutions. One is Mule. Mule exploits the 4D redundancies of light fields by using 4D transform and hexadecade trees. Another one is WASP. WASP uses depth, disparity, and sparse prediction information to reconstruct the final set of light fields. After encoding light fields, we deliver the encoded light fields to users. In literature of light field streaming, similar as coding of sparse subset of coding, only subset of subaperture images can be transmitted. There are some previous works for free viewpoint rendering application. Also streaming for refocusing application. In these works, only subset of views are transmitted, assuming that transmission of full light fields will cause a substantial startup delay. Transmission delay is an important aspect in such interactive applications. By considering interactive refocusing application, there are subaperture images at the server side. They can be stored at the cloud storage service. At the user side, user interactively refocus to a given light field content. In such application, one scenario is to render refocus image on the server and encode and transmit it to the user. Here the main challenge is interactive transmission delay. An alternative scenario is to transmit full light fields and render it on user side. In such scenario, the main challenge is startup delay. These two scenarios are simulated and analyzed in this given reference paper. More recently, Fourier disparity layer representation was used to stream light fields using a binary hierarchical scheme. To transmit the layers in a scalable fashion and to exploit their redundancies, the paper proposed a binary hierarchical scheme that first encodes a compound layer equals to the sum of all layers. An optimization of this scheme was also developed for an adaptive streaming scenario. Second topic is 360-degree video. In 360-degree video delivery pipeline, the first step is acquisition, where an omnidirectional camera captures the scene. After capturing, we divide a given 360-degree video into tiles, and each tile is encoded and transmitted to the user or to the decoder side, where we can render the viewport of a head-mounted display. "360-degree videos are usually stored with a rectangular representation. However, 360-degree videos are captured and viewed as a spherical representation. This representation has some distortion on the pole regions of the sphere. Also, this area contains redundant pixels, and we need to exploit redundant pixels in video coding. Also, in 360-degree video, a small portion of 360-degree video is rendered by virtual reality devices. Therefore, we need to have very high resolution of video in order to have a good quality of video experience. Second, we need to consider interactive consumption nature of 360-degree video. For compression, one solution is to use viewport-based representations to have a cost-effective solution. On this slide, you can see truncated pyramid projection. In this representation, the overall bitrate is reducing without decreasing the quality of the viewport. In a video streaming scenario, the client can request one of the video versions according to the user's orientation. The advantage of such system is that even the client wrongly predicts the user orientation, video can still be rendered in the user's viewport with low quality. Another solution is a tile-based streaming system. In this system, we divide a given video into tiles, encode and store them on the server side. At the client side, the 360-degree video player can request the inside viewport tiles with high quality and outside viewport tiles with low quality. In such system, each tile is encoded with a set of target bit rates and resolutions. Therefore, optimization of resources such as storage and encoding are necessary at the server side. There are different techniques for combining of resolution and target bit rates. One example work addressed this problem and focus on server-side optimization in order to find optimal coding parameters, bitrate, and resolution. In this method, by using the content category of 360-degree video, we can predict encoding and storage cost. A given constraint by the user, we estimate cost-optimal encoding parameters using linear optimization before video encoding. Therefore, we have all the parameters before compressing a given video. Later, this work was extended to consider more diverse 360-degree videos and network devices such as Wi-Fi, 5G, and wired connection, as well as viewing trajectories with different user devices such as tablet, head-mounted display, and laptop. With this system, 360-degree video streaming can be optimized at the server side in order to achieve high-quality video streaming service. Until now, we use fixed tiling structure. As you can see on this slide, in order to achieve cost-efficient video streaming service, different tiling structure can be also used by merging some tiles. By merging tiles, we can exploit redundant pixels better with standard coding methods like HEVC. And by using small tile sizes, we can use view per area in an effective way and improve the perceived video quality. Therefore, we need to determine optimal tiling structure. To find optimal tiling structure, we need to have a quality metric in streaming system that consider visual attention map. And visual attention map identifies the most probable regions that viewer might use it. We should take plane to sphere distortion into account in our quality measurement as well. By using visual attention, we can also distribute a given total bitrate to the tiles. On this slide, you can see a viewport region for one user on your left side, and on your right side, when we gather viewport regions from several users, we can obtain visual attention map as you can see on your right hand side. By using visual attention, we can distribute a given total bandwidth to the tiles. For example, we can encode the tiles which have a high visual attention value with high bitrate levels, and we can encode the low visual attention regions with low target bitrate levels. As I mentioned previously, in order to optimize tiling structure, we need to have a quality metric that considers visual attention. For this, we can extend well-known distortion measurement called mean square error to visual attention-based mean square error by considering visual attention of the viewport area. We should also take plane to sphere distortion into account in our formulation. With using the formulated visual attention, spherical weighted mean square error, we can determine optimal tiling scheme at a given target bitrate. Now last topic is volumetric video. After acquisition and reconstruction, we need to have volumetric video representation to deliver to users. Common representations for volumetric video are polygon meshes or point clouds. In scientific experiments, point cloud data score well in experiments comparing visual quality, bitrate, and compression performance, as well as computational complexity. Due to an increased interest from the industry, on point clouds, MPEG issued a call for proposal on point cloud coding. Based on the responses made to this call for proposal, two different coding techniques were selected for point cloud compression, called PCC. One is a geometry-based PCC, GPCC, and video-based PCC, called VPCC. Two reference software were also developed, one for categories 1 and 3, TMC13, and another one for category 2, TMC2. Let's first look at the geometry-based PCC, called GPCC. GPCC utilizes data structures such as an octree that describes the point location in 3D space. The points have an internal integer values converted from a floating point representation. This conversion is conceptually similar to voxelization of the input point cloud and can be achieved by scaling, translation, and rounding. VPCC coding approach is based on 3D to 2D projections. These solutions generates 3D surface segments by dividing the point cloud into number of connected regions, called 3D patches. Then each 3D patch projects independently into a 2D patch. This process results in a collection of metadata information. One is a binary image called occupancy map, which signals whether a pixel corresponds to a valid 3D projected point. Second, a geometry image that contains the depth information. And this is the distance between each point to location with the projected plane. And third one is attribute images with RGB image. And each output is encoded with standard video codec and transmitted to the user. There are also volumetric video coding activities for polygon mesh representation. For example, Google has released Draco codec, and Draco codec uses the connectivity coding based on edge breaker algorithm. There is also MPEG standardization activities for polygon mesh coding using VPCC codec. The main target is to extend VPCC to polygon mesh representation. We also need to deliver volumetric videos to users. A given number of objects in a scene, one solution of delivery of volumetric video is to use information on the user's position and focus, the available bandwidth, and the client's buffer status to decide upon the most appropriate quality representation of each object. In this scenario, we can allocate bitrate using 1. Distance to user, 2. Size of the object, and 3. Visual area within the viewport. Current MPEG Immersive, called MPEG-I, is studying immersive imaging technology. This study ranges from 360-degree video to free navigation with volumetric video and light field. Similar as VPCC, the new standardization focus on supplemental enhancement information, motion parallax with 3DOF plus and 6DOF solutions. The input of MPEG-I pipeline is the number of cameras and depth sensor. Pre-processing block which can apply several techniques to generate suitable representation for encoding. For example, as a pre-processing, color correction, blending, depth estimation, patch generation, point cloud generation, and other representation. And at the user side, the view position is rendered using view renderer software, such as view synthesis, with the help of metadata and decoded bitstream. The metadata can be collection of disocclusion patches, as can be seen on the top of the video. This metadata can be used for view synthesis for improving the rendering quality. MPEG-I currently has two important reference softwares. One is the Enhanced Depth Estimation reference software, and this software estimates depth maps for immersive imaging for 3DOF plus and 6DOF applications. Second is view synthesis software, and this is a view synthesis software called Immersive Video, TMIV, to synthesize a virtual view for 3DOF plus and 6DOF applications. And as a summary, today we talk about content delivery systems for traditional digital imaging, and we talk about content delivery mechanisms such as compression, coding standards, and some example works, and streaming solutions. And we focus on three different immersive imaging modalities: light fields, omnidirectional imaging, and volumetric video. And next part of this tutorial is how are the immersive imaging data rendered and displayed at the receiver side.
In this part, we are first going to see the main rendering algorithms used to visualize immersive imaging data, and then see some examples of displays specifically designed for immersive imaging. So here is the outline for this part. First, we will see the different rendering algorithms corresponding to the different imaging modalities considered in this presentation: light fields, omnidirectional imaging, point clouds, and texture meshes. Second, we will introduce display technologies, which will divide in two categories: planar displays and head-mounted displays. First, let's have a look at the free viewpoint rendering algorithm from two parallel planes light fields. And this is the most common and simple rendering algorithm for light fields, which has been described in the first light field papers presented at SIGGRAPH nearly 25 years ago now. We can see an example of results from the light field rendering paper in the videos playing. And at the time, being able to perform free viewpoint rendering in real time with such complex lighting effects was really a breakthrough. The idea is that we have two parallel planes light field available, and we know the position of the two planes in space. And if we consider a virtual camera for which we know the intrinsics and extrinsics parameters, Then we can project a ray corresponding to a pixel into the two light field planes. And then we compute the color value for that pixel in the rendered image using a bilinear interpolation for each plane, which makes it a quadrilinear interpolation. If we know the planoptic intrinsics matrix for the light fields that was introduced in part 2, it's very easy to compute the 4D light field pixels coordinates. And then we can see an example of these pixels being fetched from a light field highlighted in white in the video in the middle. For omnidirectional imaging, there are two main steps for rendering a novel viewpoint, and the goal is to project the chosen viewport onto the planar image used to store the omnidirectional data. So if we consider the viewport that we want to render, it will have the same center as the omnidirectional sphere, and its orientation is also known. For example, it can come from a head-mounted display. And then the first step is to project that viewport onto the sphere. And the second step is to project that portion of the sphere onto the planar image using the appropriate sphere projection. In this example, we have an equirectangular projection image on the left, and we can see that even if we want a square viewport, the shape of the viewport on the planar image is not square anymore due to the deformation of the sphere projection. As we will explain later in this part, if the viewport is rendered in a head-mounted display, we will need an efficient implementation of the algorithm running at high frame rates, which typically involves implementing these algorithms on a GPU. Now for rendering point clouds, the challenge is that point clouds can consist in a very large number of points. So usually we will consider a hierarchical representation of the point cloud, for example obtained with a KD3 decomposition. Then we need to decide which points are visible from the chosen viewport that we want to render. So that means discarding points outside the viewport frustum or occluded by other points closer to the virtual camera, for example. And if we have a big point cloud, we don't want to check this for every point, which is why the hierarchical representation is useful, because we can first check points at the coarse level, and if a point is visible at the coarse level, then we can check the corresponding finer levels. Once we know if a point is visible, we can draw it in the rendered image, typically using a splat, which is like a small surface. And there are several parameters that we can manipulate to control the render. For example, the size of the splat is shown on the top right image, and this can be adjusted, for example, depending on the distance between the virtual camera and the point cloud. Also, the shape of the splat is shown on the bottom left. And finally, the orientation of the splat that we can, for example, orientate towards the normal of the point clouds, as shown on the bottom right. So in this bottom right image, we have on the left the splats which are all oriented towards the camera, and on the right they follow the orientation of the normal, and we can see that the edge of the nose, for example, is more straight. So in conclusion, each of these parameters obviously has a strong impact on the final render quality. For textured meshes, we follow similar steps as for the point cloud rendering. We first need to compute which geometric elements of the mesh are visible for the viewport we want to render, and then compute the corresponding texture. So for example, the visibility of the vertices and faces of the mesh, shown here on the left, can be decided by checking that they first are in the viewport frustum, and that the face is correctly oriented towards the viewport, or that there are no other elements occluding this face. Then the texture is drawn on the visible surface from the texture atlas using the UV map. Possibly we can also use the information about the lighting condition from the material file. Volumetric content is typically visualized in a head-mounted display, so similarly to omnidirectional content, we need an efficient implementation for the rendering algorithm capable to run at high frame rates. In this example, we are showing the rendering method designed for the VR experiment called Welcome to Light Fields from Google, which we already mentioned in this presentation and is based on spherical light fields. So it is an interesting example because it is in a way a combination of the previous rendering methods. So again, if we consider a virtual camera, then we can project a ray corresponding to one of the rendered image pixels into the surrounding sphere. And on this sphere, we know the position of the cameras used to capture the light field data. So centered at each camera position, we will have a disk, which will be intersected by the ray at the position, which is mapped to a weight from the kernel, such that at the center of the disk, the weight is 1 and 0 at the edge. So this is in a way replacing the bilinear interpolation used in the two-parallel plane rendering. And then the ray is projected onto the image corresponding to that disk to fetch the color information. And the image itself is mapped onto a triangle mesh corresponding to the scene geometry. So the final value of the pixel in our novel viewport is the weighted sum of all the disks intersected by the ray. So in this example, contrary to omnidirectional imaging, for example, there is a sense of parallax when looking around with the final rendered images, which corresponds to 3D OF+. Finally, we wanted to mention that, as in many areas of computer vision and graphics, we can see powerful methods emerging based on deep learning technology. And we don't have time to get into the details of each method, but the main idea is generally to use a deep network to estimate a volumetric representation of a scene from sparse input viewpoints, which usually corresponds to volumetric content capture. And this recent trend is possible thanks to differentiable rendering, which allows to backpropagate the rendered image error through the network to train this network. So now that we've seen different ways of rendering light fields, omnidirectional imaging, and volumetric videos, my colleague Emin is going to introduce different displays designed to visualize immersive imaging data.
So, we have just had a look at the rendering algorithms for different immersive imaging modalities. Let's start discussing the display devices with 2D screens. As we mentioned in part 2, the 3D scene can be recorded as light fields with lenslet arrays. Using a similar lenslet array mechanism, these recorded pixel values can be projected back to 3D world, forming a 3D image hanging in the air. This process is called integral imaging, and it is essentially the reverse operation of a planoptic camera such as light-through. Nevertheless, there is a caveat. This 3D image is formed at a fixed distance, as the light rays from the display would only converge at a single location. Therefore, the viewers need to be looking at the display at this fixed distance to see the 3D image generated. Another technique is to use optical modules similar to projectors, which is shown on the right-hand side figure. This system creates parallax. Looking at this again from a fixed distance, the viewers will get an impression of seeing the light field and the 3D image on the air, as shown on the video here, so that whenever you are standing at a fixed distance from this display, that you will feel that there is a fish hanging in the midair. Another option for displaying light fields is using a holographic display. As an example, the looking glass is one of such displays. As you can see from the sample videos here on this slide, the device enables the viewer to look from many different angles and provides a 3D imagery using a technique called multiscopy. This way the viewers can see 3D imagery as if it is floating in the air. Although the devices that we just discussed are somewhat more special, some other devices that we use to display immersive imagery are very familiar. Smartphones and tablets are such devices that many people own and use in their daily lives. Since they have a back camera and a display, they are perfect devices for video-based augmented reality. Here we see a few examples of the applications from Pokemon Go, which is a popular mobile AR game, to the museum guide prototype we mentioned in the earlier slides, to IKEA application, which lets you place augmented reality furniture in your apartment. Although these displays are affordable and easily accessible, they have a very limited field of view. Nevertheless, we can predict that these will be the devices which would make AR more popular due to their availability. Next, we have head-mounted displays, or HMDs, for the display of immersive imagery. There are many different companies now who make HMDs for these purposes. Here we list a few of them. One of the first companies to build a VR set was Oculus. Now Oculus has several models, as does HTC with their own Vive series. There's also PlayStation VR, Valve Index, and many others. Most of these devices now provide at least full HD displays with 72 to 120 FPS frame rates. So rendering needs to be fast, and these devices need to have good algorithm design and hardware at the same time. Most of these devices, except for Oculus Quest, need to be connected to a powerful VR-ready PC for their rendering needs. Most HMDs for virtual reality either has various sensors embedded in the hardware or needs external tracking. With the help of these measurement units and external tracking methods, the HMDs can do head tracking and in some cases eye tracking as well. As we will also discuss in the next part, human eyes are not made very close to the human face. However, most of the HMDs, as we know, we've seen from the pictures, they have a display really close to your face. Therefore, lenses are used to map the display to a distance which is more comfortable for the eyes and also gives a wider field of view, as shown in the figure below. In most cases, these displays provide stereoscopic 3D with high frame rates, more than 90 Hz. Additionally, those displays with eye tracking capabilities can also provide foveated rendering, that is, the regions in which eye focuses are made of high resolution imagery, and the rest of the image is made up of low resolution, as shown in the figure above. There are also near-eye light field displays which can provide a virtual reality experience. As you can see from the figure above and from the video, these displays have lens-led arrays, and they work similar to the integral imaging techniques. As we know from earlier slides, viewers needed to be at a fixed distance to see the 3D images. In this case, the distance from the viewer's eyes is fixed due to the design of the near-eye light field HMDs. Therefore, the viewer's eyes are naturally at a comfortable distance to see 3D imagery. This approach is also further improved by increasing the number of display panels from 1 to 2. With 2 LCD panels, one that is closer to human eye and another which is a bit farther away from the human eye, the eyes can actually focus on the physical surface of these two different displays. This in turn helps avoid divergence accommodation conflicts, which we will further discuss in the next part as well. Since the eye is given different options for focusing or accommodation on two different displays, it feels more natural to the human eyes. For augmented reality, proper visualization of the immersive imagery is more complicated than that of virtual reality. Since the real world is also visible through either a see-through display or a video-based AR display, the position of the HMD needs to be tracked accurately. And this tracking has to be relative to the actual environment to allow a reliable alignment of the virtual objects with the real scene. Since the displays more commonly used for AR right now are see-through displays, we will focus on see-through optics in this slide and in this tutorial. For these HMDs, there is a translucent screen where the virtual content is projected using projectors or light engines, and real world is also visible from these translucent glasses. There are mainly two HMDs available for AR, commonly used for AR applications and scientific research. These are Microsoft HoloLens and Magic Leap's Magic Leap 1. As mentioned in the previous slide, these devices are see-through AR displays, that is, they do not block viewers' sight, but add the virtual objects over it. There are also other products or prototypes who aim to go for a sleeker glasses look. However, they mostly do not provide full AR options these HMDs do. HoloLens 2 is one of the leading HMDs for AR. It has these technical specifications written on the left column. It has head, eye, and hand tracking capabilities with an increased field of view of 52 degrees. Compared to human visual range, this field of view can be still noticed as shown here in the bottom figure. The visuals are not solid and they are ghost-like for the moment, and they convey a sense of holograms from science fiction movies. Nevertheless, having many capabilities, it is one of the leading HMDs for augmented reality applications. Magic Leap's Magic Leap 1 is the most capable competitor to Microsoft HoloLens series. Here you see a sample video below using volumetric videos. Most of its specifications are similar to that of HoloLens, except for the increased RAM and storage. Similar to HoloLens, the visuals are not completely solid and kind of see-through or ghost-like. Its one difference from HoloLens is the presence of a separate variable computer part, which is shown in the figure below. This helps reduce the weight of the headset and make the headset a bit lighter. But other than that, they are mostly similar in use and also hours of uses. In summary, in this part, we've discussed how immersive imaging data are rendered and how immersive imaging outputs are displayed using either 2D screens or head-mounted displays. In the next part, we will cover visual perception of these immersive imaging data and the quality assessment topics. This concludes part 4. Thank you for listening. Hello everyone, and welcome to the last part of this tutorial, part 5, Perception and Quality Evaluation. In this part, we will try to answer the following questions. What are the relevant visual perception principles? How do we assess the quality of the processed media? And how does visual attention change for immersive imaging? Therefore, in this part, we will first discuss the visual perception. We will follow that by describing the quality assessment methods for light fields, omnidirectional imaging, and volumetric videos. Then lastly, we will discuss visual attention for the different imaging modalities. Although there are many different approaches to understand the human visual system, for this tutorial, let's divide our visual system into two parts, trying to answer these two questions. How do we see and how do we perceive? For the physical sensory part of the system that is seeing, we know that the process starts by light rays making their ways into our eyes, hitting to our ganglion cells, which then connect to the bipolar cells and to our photoreceptors. While rod cells work for us to understand the light in the environment, cone cells help us to see color. These signals are then transmitted through the central nervous system. Another very important organ for the visual system is the brain, where perception happens in the primary visual cortex with the help of other brain functions, such as memory. The response of human visual system for digital imaging has been studied thoroughly in the last 2 decades for traditional 2D imaging systems. We know that the contrast sensitivity of human perception differs by the background luminance and the frequency as shown on the figure on the left. And we also know that our visual perception system can perceive images as colored even though the color information is heavily sampled as shown in the figure in the right. So that it is actually a grayscale image, but there is only a colored grid, so our brains perceive it as a colored image. In this tutorial, we focus on the parts which are more relevant for the immersive imaging technologies. One of the things that would be relevant for immersive imaging technologies is the field of view and visual angle concepts. The field of view is a region that we can see while looking at a single point in space. The term also has been used to describe the region or angle that we can see through a display system in the previous parts of this tutorial. Here we have two figures on the screen, roughly corresponds to the same thing. The figure above shows the areas of central and peripheral regions of the human field of view. The figure below also shows the same angles in a different representation. Throughout these regions, the acuity, visual acuity, and color perception changes. Let's have a look at these regions, starting from the center and going outwards. Central part is the part where the visual acuity is the strongest. Around them, so that we have the symbol recognition, text recognition, and a lot of things. Around them, going towards outside, we have decreasing visual acuity and decreasing color vision, as the cone cells are mostly gathered in the central region. After some point, in the far peripheral parts, shapes are not anymore intelligible, and we can only determine if there is a movement. So if we are standing at a particular location, say on a dirt road like this one, with trees by the sides, as shown here in this picture, our eyes actually see something similar to this. So our color vision is generally focused on the center, and also our visual acuity is the strongest in the center part. While going towards the edges, we start to lose color vision as well as visual acuity. Towards the edge of our fields, we don't perceive the shapes fully and it gets really blurry. Nevertheless, thanks to our brains, our perception completes the picture when we look around and completes the whole picture. Thus, we still perceive the scene without any loss of color or texture. The complete field of view for human visual system is around 125 degrees vertically and 170 degrees horizontally. And if we consider only binocular field of view, it comes down to less than 140 degrees. As we have seen in the previous part, the current HMDs for augmented reality have around 50 degrees in field of view, as shown here in the dashed parts. So within the human's field of view, they correspond to only a portion of our field of view. Another term which we need to understand is the pixel per degree. So let's have a look at the figure down here. So imagine that we are looking at the display. So this is a monitor on your desk, for example, which you're staring at it from 50 centimeters distance, or it could be your television at your living room, which you're staring at 1.5 meters or 2 meters distance. Pixel per degree is a measure that gives us how many pixels in 1 degree visual angle. So that it is, the higher the pixel per degree is, the higher would be the quality. And this is especially important to understand for us to display quality and rendering quality for HMDs and many volumetric video applications. Due to practical reasons, HMD screens are placed very close to the human eye, as shown in the right figure here on the rightmost part. However, our eyes cannot keep things very close to our head in focus. That is, our eyes are not capable to accommodate to that plane. The minimum distance for accommodation is around 10 centimeters for adults, so things need to be at least 10 centimeters apart from our eyes for our eyes to be able to focus to it. So in order to solve this problem, a lens is placed between the HMD's display and the human eye, as shown in the top figure, and also as shown in the sketch in the center below. So this increases the perceived distance between the eye and the virtual screen and helps eye accommodate. And it also increases the field of view for the screen displays, so that it gives us a better and wider field of view for the HMD. Since in most cases we are considering the visualization of 3D objects on still planar or piecewise planar surfaces, the limitations of the traditional stereo 3D imaging are valid here as well. One such limitation is divergence accommodation conflict. To see a 3D object in the real world, our eyes do two different things. First is the accommodation of the lens. That is, our eyes focus on a certain plane, and this is monocular, so each eye does this by itself. Second is vergence. Our gaze, or our eyes also, converge on an object that is binocular, as we use both eyes to be able to do this. When we focus on the display, our eyes accommodate on the distance of the display, which is shown by the arc here on the figure on the left. However, they converge either slightly closer or farther because the virtual object that is shown on the HMD, for example, are either closer to the eye or farther from the eye. So this causes the conflict, and this might cause an uneasy feeling or headache in the worst case. Another important aspect to consider is the low angular resolution the HMDs have right now. Think about these two images. The bigger one, or the closer one, seems to be pixelated compared to the one below, which one presumably farther away. The reason for that is that the pixels per degree is not high enough so that we don't experience a smooth image without any pixelation. If the pixel per degree value increases, the image becomes smoother. Since the distance between the eyes and the HMDs are very small, the HMDs need to be built with very high resolution displays to overcome this problem. Okay, so having a look at the relevant visual perception concepts and possible problems that we might face, let's move on to a practical consideration for immersive imaging systems: quality assessment. Quality assessment is a necessary step to ensure an adequate level of service and user satisfaction. In the context of imaging, the quality can be defined as the set of inherent characteristics that we use to evaluate the excellence or the goodness of the visual stimulus in question. The signal and image processing field defines another term that is quality of experience, as a degree of delight or annoyance of the user of an application or service. So this is a bit more generic term. It's not really focused on visuals, but it is generally defined as the quality of experience of a service. Still, it is an indicative definition. So this is not a very hard task for us humans. We can definitely determine the level of quality for these two images shown here on the right side of the slide. So the image below is not a good quality, it's poor, but the one above, it is really good quality, very good quality. You don't see any compression artifacts or any artifacts. So this is really easy for humans, but it is not really straightforward for computers. So the quality is subjective by definition, and therefore the best way for quality assessment it would be through subjective experiments, in which the participants were asked to determine the level of quality or the level of impairment per stimulus, and then we record the participant results, the participant responses. However, it is a very expensive operation in both time and resources, because both the instructor and also the participants spend a lot of time, and also there's a lot of resources spent for this operation. And running subjective experiments properly needs expertise and instructor guidance. To bypass the need for subjective quality assessment, the image processing field has been working hard to develop automatic quality estimation methods, which is also known as objective quality assessment metrics. Making computations on the pixel values of images and videos, these type of metrics can determine the quality level of a visual sample very fast. And these metrics generally work well if they only consider a specific type of distortion, such as compression, for example. On the other hand, for various distortion types, they might not work that well. For example, the figure here shows various images with the same mean squared error from the reference, so that you have a reference, undistorted, uncompressed reference, and then you add some kind of distortions. It could be blur, it could be compression or blocking, it could be noise, and these images all have the same level of mean squared error, but we all perceive them differently. So as far as MSE is concerned, these images have the same error, but to us, they are not the same. So the objective quality metrics try to tackle this problem. The objective quality metrics can be based on various algorithms. Most commonly used ones are the metrics based on simple arithmetic differences or structural similarity, information theory, or natural image statistics. Or they can be specifically designed to determine the distances between different colors or different color spaces, that is, color metrics. The objective quality metrics can be classified according to the presence of the availability of undistorted pristine reference sample. There are three categories for that: full reference, reduced reference, and no reference. In this tutorial, we will mostly go over the full reference quality assessment methods. Even though I believe that many of the listeners are already familiar with the fundamentals of image quality assessment, to keep everyone in the loop, I would like to just provide an example of a very simple full reference quality assessment method, that is mean squared error. So the mean squared error takes two different images and finds a pixel-wise error in those image pixel values and computes the square of the pixel-wise error and takes the mean of this squared value. This is a very simple error-based metric, which can also be used as a quality metric, especially for applications like compression, or then it could be used in the computation of other metrics such as PSNR. While MSE is getting smaller, we can say that the test image is getting better because there is less of an error, and also vice versa. So if it is getting larger, the test image is getting worse. In the following slides, I will first mention the things to consider for subjective quality assessment, and then I will move on to objective quality assessment for different image modalities we consider in this tutorial. So I will now start with the subjective quality assessment for light field, and then move on to objective quality assessment for light field, and then subjective quality assessment for omnidirectional imaging, and so on. So let's start with the quality assessment for light fields. With light fields, the viewpoints or subaperture images to consider increase a lot because we have 15 by 15 grid, and there are a lot of images instead of one single image for the same one scene. So this is especially true for cameras with micro lens arrays. We have a lot of extra information and we don't have a single frame or a single viewpoint anymore. Therefore, we need a new approach for subjective quality assessment. In the literature, there are two main approaches for this problem: passive approach and interactive approach. Passive approach aims to provide the participant with a set of pre-rendered images or selected animations. An example of this method is shown here. So you see the video here. They show these kind of spiral videos. The subaperture images of different viewpoints are ordered in a spiral or snail model, and they are shown as videos. So this video shows you a paired comparison test visual. So participants are asked to choose either one of them, which one is the better one. And the second approach is the interactive approach, in which the participants choose the viewpoint or the animation themselves using a mouse or some other things. The recent comparison study showed that the subjective quality values collected using either approach correlate very well with one another. Therefore, there is no clear advantage of one method, one approach over the other. For objective quality assessment, again, one needs to take many subaperture images into consideration. In most cases, we can assume that all these subaperture images, or the light field as a whole, goes through the same processing algorithm, such as compression or post-processing, so we can safely assume that all the subaperture images would have a similar level of distortion, or similar type of distortion. So in the literature, the quality of a light field is computed using traditional image quality estimators such as peak signal to noise ratio, PSNR, or structural similarity index, SSIM. For example, for the calculation of PSNR over light field, first, the PSNR is computed over individual Y, U, and V channels of a single subaperture image, and then a single PSNR value for a single subaperture image is found by pooling different Y, U, and V values together, and all of these values are then averaged over the whole light field, and a single PSNR value has been found for a light field. And following this framework, various existing 2D image quality metrics can also be used to estimate quality of the light field, such as WEAF or other 2D quality metrics. Let's have a look at the subjective quality assessment for omnidirectional imaging. The limitation in this case is that the medium itself is spherical and the human field of view, or that of the display device, is limited. Therefore, the participants can only see a portion of the omnidirectional content at a time, as shown in the figures here. The current approaches are to use the traditional subjective quality assessment methodologies directly on the omnidirectional data. So if you're considering a single stimulus subjective quality assessment methodology, such as absolute category rating, you don't change anything in the methodology, you just apply it as if it was just a traditional 2D imaging system. One new methodology called Modified Absolute Category Rating, or MACR, proposes to double the exposure time by showing the participants the stimulus 2 times. In the following comparative studies, although MACR increases the total amount of exposure, DSIS was found to be more statistically reliable compared to plain ACR or MACR. For the objective quality estimation of omnidirectional images and videos, there are two approaches. First approach is to use a traditional quality metrics on the projected image or video. For this purpose, the omnidirectional content is projected onto the planar format using one of the projection methods described earlier. The most popular options are equirectangular projection and cube map projection, and afterwards, the traditional 2D image or video quality metrics such as PSNR, SSIM, multi-scale SSIM, or VMAF are applied over the projected visual, and the quality values are found afterwards. The second approach is to project the image or video onto the sphere and estimate the quality on the sphere, or to use a more sphere-friendly quality metric. The main idea with these metrics is to minimize the errors that could occur due to projections and to maximize the fidelity to the original spherical data. These metrics may include spherical PSNR, that is SPH PSNR, weighted spherical PSNR, raster parabolic projection PSNR, and even Voronoi cell-based metrics. For the subjective quality assessment of volumetric videos, one has to consider that there are infinitely many viewpoints to look from. Therefore, it is similar to the light fields in that sense, in terms of having a multitude of options for the viewers. Thus, similar to the light field case, there are two main approaches, passive approach and interactive approach. In the passive approach, the participants are shown a pre-rendered video with a selected trajectory. That is, the video here shows an example for this case. The volumetric video is fixed in the position while a camera rotates around it, and then this rotation and this trajectory has been saved as a traditional 2D video. This reduces the variation between different participants by making sure that all participants see the same thing. But on the other hand, it prevents people from exploring some other viewpoints in different time frames. The second interactive approach instead lets the viewers select the viewpoint of their choosing, either using a mouse or some other interactive methods, or wearing an HMD. As mentioned in the earlier parts, volumetric videos can be shown or represented with two different representations. That is, either textured polygonal meshes or colored point clouds. Thus, objective quality assessment for volumetric videos depends on the data representation. There are three different possibilities for the quality assessment of volumetric videos. There are mesh-based metrics for meshes, point clouds metrics for point clouds, and there's also a representation agnostic approach, which I will mention the last. Polygonal mesh surfaces are essentially the data representation for 3D models in the computer graphics world, and due to their use in many computer graphics applications, such as computer-generated imagery or computer games, there are many works on the objective quality assessment of polygonal meshes originated from the computer graphics field. Most of these objective quality metrics focus on the geometry errors. These include positional errors such as RMS distance, curvature such as MSTM or MSTM2, roughness, and angles. The figures here describe the MSTM2 process, so we can just go over it very briefly and very quickly. First, a correspondence is found between the original model and the distorted model, and the distortion is found by computing the curvature differences in multiple scales, and it is pooled over the whole mesh. and then a single quality score has been found for the distorted mesh. Although most of the mesh metrics only consider geometry distortions, joint models which consider both geometry and texture also exist, and it is more relevant and more interesting for us for volumetric video quality assessment. As mentioned earlier, the textured polygonal meshes consist of a geometry, which is formed with vertices and faces, and a texture atlas. Here sample distortions are shown. On the left, we see the distortion on the geometry components, and on the right, we see the distortion on the texture atlas. The joint models generally use two different metrics for geometry distortions and texture distortions. Then, these results are summed with different weights. This gives us a joint quality measure, which would ideally show the overall distortion in viewer's satisfaction for textured polygonal meshes. While polygonal meshes keep the connectivity information in the form of vertex connections and faces, point clouds do not keep any connectivity information. Therefore, it is harder to use the same metrics as meshes, if not impossible. The point cloud metrics mostly use point-based computations and doing computations over a single point in the point cloud, and pooling all these results for the whole point cloud. Some of the state-of-the-art metrics are distance metrics computed on point-to-point, point-to-plane, or plane-to-plane differences. Let's consider that the blue points are from the distorted point cloud, while the black points are from the reference. While point-to-point difference computes the minimum distance between the closest corresponding points, shown with the blue lines here, the point-to-plane metric computes the difference considering the normal of the reference point cloud as well, so that there might be just a bit of difference, and this might end up with the different correlation levels. So these distances are then pooled using either root mean square distance, mean squared error, or Hausdorff distance, which takes the maximum value of the considered points. The only color-based difference among these metrics also rely on point-to-point correspondence. The color difference between the corresponding reference and distorted points is found with these equations per color channel. The plane-to-plane difference is based on the angular similarity between the normal of two corresponding points. For this purpose, a normal estimation algorithm might be needed in some cases, as distorted point clouds' normal information may be lost or corrupted somewhere in the content delivery chain. Instead, PCM-STM computes the quadric surface and projects a distorted point on this surface. The metric then estimates the quality based on the curvature. Nevertheless, all these metrics consider either only geometry differences or only color differences. Some very recent quality metrics jointly assess the geometry and color distortions together. PCQM, for example, which is extended from PCM-STM, is based on curvature. The metric includes color and lightness measures, and the joint quality is found by taking the weighted sum of the geometry and color features. Similarly, Viola and others also take both geometry and color into consideration. Color has been taken into account by taking the histogram of the luminance values of the points over the whole point cloud. So it is slightly different because PCQM only considers color values per point, but Viola et al. Considers color points in a histogram for over the whole point cloud. Then the joint quality is found by weighted sum of geometry and color distortion values. These studies are promising for early works, but they are built on only one quality database and need to be studied further for generality. Another approach for volumetric video quality assessment is the representation agnostic approach. In this approach, the volumetric video is rendered from various angles, and rendered images then used to compute the quality. Since the rendered images are essentially 2D images, traditional 2D image or video quality metrics are used to determine the quality of the volumetric video in this approach. The results from different viewpoints are generally pooled to get a single quality score for the whole volumetric video. There are certain advantages and disadvantages to this approach. It is advantageous because the underlying data representation is not really important at this point. The rendering-based approach is similar to human visual perception, unlike the data-based approaches. And there is already years of scientific research on 2D image and video quality assessment. So we have advantages on these sides. This approach is also disadvantages because it relies on rendering, which is an expensive operation, and different rendering parameters or cases such as lighting might affect the performance. With this, the quality assessment part is over. Now Çağrı will take over to present the visual attention part. Thanks.
After having a look at the quality assessment methods, now let's move on to the visual attention. Visual attention or saliency means what is the most prominent in the scene, what is basically attracting us. By understanding the saliency regions within a visual stimulus, we can optimize image or video systems. This is in particular more important for immersive imaging, as they require huge amount of data to obtain high quality of experience. There are several applications that can use visual attention. For example, we can use to segment silent areas using segmentations. We can use to crop most salient regions. We can use to compress videos using visual attention. We can also measure video quality using visual attention and post-production. Visual attention map highlights the most important regions with a probability map. As you can see on this slide, saliency map with overlay image. We can obtain visual saliency map using subjective experiments or computational models. Subjective experiments are expensive in terms of time and effort. Computational models can be fast and can be used in real-time video systems. However, we must gather user data that we can use computational saliency models. We can use user data to train neural network and test the trained models. How do we collect visual attention data? The most widely used solution is to use eye tracking device. By using eye tracking device, we can capture eye tracking data while showing the participants a stimulus. There are several options for eye tracking devices, which are range from low cost and less accurate devices like webcam to expensive and most accurate solutions like professional eye tracking setup. On this slide, you can see eye tracking data for all participants for a given visual stimulus in subjective experiments. In collected eye tracking data, we can observe two main eye movements, fixations and saccades. There are also events in the sense that they are periods for fixations and saccades. There are also other events such as blinks or smooth pursuit. If you are interested, I suggest to check the reference on the slide. Fixations are those times when our eyes essentially stop scanning about the scene, holding the center foveal vision in place so that visual system can take in detail information about what is being looked at. On the other hand, saccades are the types of eye movements used to move the fovea rapidly from one point of interest to another. Because of the fast movement during a saccade, the image on the retina is of poor quality. An important visual information collection is happened mostly during fixation period. Therefore, we only use fixations to obtain visual attention map. How do we collect visual attention? In order to obtain visual attention map, eye gaze trajectories are collected during subjective experiments. Then, we take fixations from the eye tracking data. Fixations are aggregated in a map. Fixation map is a binary map which consists of 0 and 1. That map is then convolved with a 2D Gaussian kernel to obtain visual attention map. This map can be seen on the slide as individual attention maps. As a final step, individual fixation maps are merged together, convolved with a 2D Gaussian to obtain visual attention map. Let's focus on visual attention activities in immersive technologies. As we discussed previously, emerging light fields displays support focal cues. One good example is foveated rendering system for light fields. Inspired by 4D light field display and 2D foveated image rendering techniques, the researchers in NVIDIA have built a hardware prototype for foveated light field display with a GPU-based light field rendering engine that runs in real time. This prototype system consists an eye tracking device as shown on the slide, and foveated rendering for light field can reduce computation costs without perceptual quality degradation. We can interactively refocus objects in light fields. In this context, the researchers in Trinity College Dublin investigate different interactive scenarios. This includes refocusing of the light fields to get a certain object in focus, or creating videos including frames of different focus points, that is creating a focal sweep. There are attempts for saliency modeling of light fields. Existing works focus all focus images with human labeled ground truth binary masks and the corresponding focal stacks for every light field image. One recent example uses a fusion framework that includes two CNN streams. One is for the focal stacks and another one is all focus images. The authors also use a recurrent attention network to fuse each slide in the focal stack. Experimental results show the effectiveness of this network architecture for light field saliency. Now let's talk about visual saliency or visual attention in omnidirectional imaging or 360-degree image or video. The most essential difference of human visual perception between 360-degree video and 2D video lies in visual attention. The viewing range of 360-degree video and viewing pattern are totally different from 2D video. Because of this fact, the majority of existing works on the perception models of 360-degree video focus on modeling visual attention on 360-degree video. There are works that consider head, with and without eye trajectories. Most of these experiments show that users spend their time in equatorial region. In another work, the researchers analyze visual attention from head-mounted displays, viewport center location, and visual attention from eye tracking data. After the investigation with probability density function, the researchers in this paper propose a new Gaussian filter that can be applied to the viewport center. This is in particular important for the head-mounted displays that doesn't have embedded eye tracking device. On this slide, you can see visual attention map with Gaussian filter on center of the viewport. Now you can see visual attention map with a new filter. Now you can see visual attention obtained on eye tracking data. We can see that using the new filter together with the center of the viewport provides better results compared to using the Gaussian filter. At this point, I also suggest the second reference paper that investigate other Gaussian filters. After obtaining visual attention map, we can use it with different techniques such as quality assessment. As described earlier, we can use Voronoi cell-based quality estimation framework and weight the objective quality score such as VMAF, PSNR or SSIM to obtain more perceptual quality score. This way, we can consider the silent area that user look at them. Because of the spherical nature of 360-degree video, we need new saliency map estimation methods. Salient 360 Grand Challenge at the ICME 2017 and 2018 foster further research works in this domain by providing a benchmark platform for visual attention models. We can see two early saliency estimation models for 360-degree images. Both approaches focus on undistorted patches using cubic projections and fine-tune the existing 2D saliency estimation models such as SALNet and SALGAN. There are more recent attempts at visual saliency estimation for omnidirectional imaging. Current focus in this area is change from obtaining undistorted patches with CubeMap for modeling to new convolutional neural networks that consider distortion of 360-degree video input images. There are techniques that focus on the pixel distortions in deep learning, such as panoramic convolutions, cube padding, spherical CNN, and estimating tangent images. As a last topic of this part, I will discuss visual attention of volumetric video. There is a recent example of visual attention work in this area for volumetric video. In this study, the researcher developed a custom environment in Unity 3D and they conduct an eye tracking experiment with static 3D point cloud models. As you can see on this slide, visual attention is attracted by low-level features such as edges and contrast, and high-level features such as faces. Similarly, another attempt is to estimate visual attention for polygon meshes with subjective and objective experiments. One of the interesting analysis of this paper is analysis of depth and center bias. The user studies in this paper show that the center bias exists in visual attention of meshes, but there is no depth bias for visual attention of meshes. For other analysis, I would suggest for checking the reference paper on the slide. In this part, we discuss the basic principles of the human visual perception and how it relates to various immersive imaging technologies. We also discuss different quality assessment methods and how we use visual attention for 3 different imaging modalities: light fields, omnidirectional imaging, and volumetric videos. We believe that in near future, we will see that the boundaries between these modalities will start to disappear. Many thanks for all who listen to this tutorial. Please check out our tutorial website if you wish to have a look at all the references we have used in these slides.